Introduction to functions. The concept of a function ranks near the top of the list in terms of important algebra concepts. So this year we're going to spend a ton of time with functions. This unit we're just going to kind of get the basics of them, and then later on we're going to spend some time with all different types of functions. So, and it says almost all higher level mathematical modeling is based on the function concept. Okay, so the concept is relatively simple. The definition of a function, and you've dealt with functions all along, you just never called them that. So it says a function is a clearly defined rule that converts an input into exactly one output. So there's your function definition right there. We're going to refer back to that a lot. The rules often come in the form of equations, graphs, tables, and verbal descriptions. Now you've dealt with all of those four things. Okay, so let's look at this first example, and it says consider the function rule. And now let's read it. What do they mean by this rule? It says multiply the input by 2 and then subtract 1 to get the output. All right, so that's our rule. And it says fill in the table below for inputs and outputs. Inputs are often designated by X and outputs by Y. So they've set up this table for us, our inputs, or our list of X's. We're going to do some calculations according to the rule that was given up here. And then we're going to come out with our Y values that go along with those given X values. So the first one, well, what if my input is 0? Well, the rule says to multiply the input by 2. So I multiply that input as 0 by 2, and then subtract 1 to get the output. So 2 times 0 minus 1, the output, what comes out of that rule, is -1 if we put a 0 in. Well, what if we put a 1 in as our input? 2 times 1, because our rule says multiply the input by 1 and subtract 1. So we end up, that one spits out a 1. Well, what if we put in or input a 2 into our function rule? 2 times 2 minus 1. So that's 4 minus 1, that's 3. And then finally, well, what if I have an input of 3 as my X value? So I'd still do that same function rule that they're telling us to do, 6 minus 1, which is 5. So I have this list of inputs and its corresponding outputs. And now, with any table, look for some patterns. Look to see what's happening here in the outputs. Look to see what's happening here with the inputs. You're going to start to train your eye and train your brain to always look for patterns. So notice some of the patterns on the outputs and the inputs, and keep that in mind. Keep those in mind right now, any types of thoughts that you have. And let's see what comes of those thoughts. So let's go over here to C. We're going to go back to B. I want to go to this graphical representation first. So let me get this little guy out of here. I don't know why that's there. So, okay. So let's graph function rule on this graph paper below. We got to use the table. So we've got our list of X's and we've got our corresponding Y's. So my first point that I've got to plot is 0, -1. Okay, so that's my first. So 0, -1 would be right there. And then the next one is 1, 1. Okay, input of 1 and an output of 1. So 1, 1. Then we have 2, 3 is my second one. 1, 2, 3. Okay, that came from right here, 2, 3. That's the second point. Now we're going to plot this last point, 3, 5. So 1, 2, 3, 1, 2, 5. Okay, and now let's connect that. And let's notice some things about this line. What do you notice? So you can see where it starts here. It starts down here at -1. and then maybe to go from one point to the next, what do we have to do? We have to go up 2 and over 1, up 2 and over 1. So that you should start to see a pattern that's happening with that line as well. Now think back to what you thought about with your inputs and your outputs and the patterns you saw in that table compared to the patterns that you are seeing here on this line. Some things should start to click here. So what is this? Up 2 over 1, up 2 over 1. What are we doing here? Up 2 over 1. What was this point down here? Oh, we should start thinking of slope or rate of change, our y-intercept. You should have noticed a pattern of adding 2 as we were going down this, and a pattern of adding 1. Wow, they're all starting to relate to each other. Now let's write the equation that gives this rule in symbolic form. So write an equation. So y equals mx plus b should kind of come to your head. So let's see. Y equals, we found the slope to be 2x plus, and what was our y-intercept? A -1. 2x plus a -1. Well, wow, back up here in our rule, it says that our rule says multiply the input by 2 and then subtract 1. Isn't that exactly what's happening down here? To get our output, we're multiplying our input by 2 and subtracting 1. So those patterns are not a coincidence. Okay? Pretty cool. So in exercise 2, we've got a different function. It says in the function rule from number 1, I lied. We're using the same function in this one. We've changed functions down in number 3. So for what input, okay, so they're looking for the input, they're looking for the x value, would be needed to produce an output of 17. So we've got to find the y. And then they ask the question, why is it harder to find an input when you have an output than finding an output when you have an input? I think it's just as easy to find either one, especially if we have the rule. So we said our rule was 2x minus 1. And they're saying, okay, what input? So we're looking for the x if we know the y. The y is 17. 2 times what minus 1 gives us 17. And if we solve that for x, we get 18 equals 2x, and x equals 9. So there's our output. There's our input. Okay, we were asked to find the input of 9 if we had an output of 17, and that's the point, the x, comma, y. All right, in exercise 3, we change. It says a function rule takes an input n, so they just changed the input to n, and converts an output y. Now here comes the rule. By increasing 1/2 of the input by 10. So this is where we need to do our translating. So our output is y. It says by increasing half of the input by 10. Half of the input, okay, by 10. Increasing, so plus 10. Sorry guys, the printer's going off and the phone at the same time. Now they're asking us to use it. It says determine the output for this rule when the input is 50. So they want the output when the input is 50. So half of 50 is 25 plus 10. The output is going to be 35. So you've done this before, okay? Now we're just talking about pieces of a function, the inputs and the outputs, instead of just the x's and the y's. Okay, so go ahead. And it says function rules don't always appear to be in numerical nature. Okay, so as long as you have an input, it says simply have to return a single output for a given input. It's a function. Okay, so let's look at this table below. We've got a child's name with their birth month. So the child's name in this case is the input and the output is the birth month. It says, why can we consider this rule a function? Well, go back to that definition. Okay, for each child, which is considered our input, okay, there is one, okay, month that he or she is born. There is 1 month that he or she is born. That's our output. So it fits the definition of the function. So what is the output when the input is Rosie? So when the input is Rosie, the output is her birth month, February. Okay. It says find all inputs that give an output of May. Okay. Find all inputs that give an output of May. So I see May right here and May right there. So those two inputs would be Zeke and Nico. It says, why does this not violate the definition of a function, even though there are two answers? Okay, so this does not violate that definition of a function because each input still has only one output. Each input only has one output. Okay, and it says there's no condition on a function that insists that each output has only one input. Okay, just each input can only have one output. I always like to say you can't have any X repeaters. No repeat inputs. Okay, that's the definition for your function. It's sort of said in a simpler sense. It says functions are helpful to model things in the real world. So let's look at this example in this kind of cool graph of Charlene as she walks to school, and her distance from school in blocks is given as a function of time, okay, time in minutes, and her distance from school in blocks. So before I jump into those questions, let's take a look to examine what exactly is happening on our graph here. So over here on the y-axis, we have our distance in blocks. Down here in the x-axis, we have our time spent walking in minutes. And right here, we know that that's 0. And then we have a 5, a 10, and a 15. So I can make the assumption that each one of those is worth 1 minute. And then 0 here, and then I go by tens. And then I can, again, make another assumption that these are counting by twos. So it's important to know the scale before you start to answer some questions. It says, how far does Charlene start off from school? So at 0 time, okay, at 0 minutes, she's right here. So that's 22 blocks she is from school. What is her distance from school after she has been walking for 4 minutes? So I would go to 4 minutes and go meet the graph, and what is her distance there? She is 14 blocks from school after walking for 4 minutes. And then part C says, after walking for 6 minutes, Charlene stops to look for her subway pass. So she's stopping after she's walked for 6 minutes. So it's 6 minutes, go meet the graph, and you can see what's happening here. Okay, it's leveled off. So she's not getting closer to school. Okay, she's standing there looking for her subway pass. So it says, how long does she stop for? Okay, so from 6 minutes down here to 9 minutes, 6 to 9 minutes. So that's a total of 3 minutes is how long she's stopping for. Okay. And part D says, then Charlene walked to the subway station before heading to school on the subway. How many blocks did she walk to the subway? So that's this little distance right here. Okay. So she stopped. She was looking for a subway pass. Then she had to walk to the subway station. And that little distance goes from 10 blocks to 12 blocks. Okay. 10 to 12 blocks, so that's a total of 2 blocks, okay, to the subway station. And then part E says, how long did it take for her to get to school once she got on the train? So you can make that assumption that this piece right here, okay, is her travel time on the train. And we're looking for how long. So that's our time. So that was 11 minutes down here to 15 minutes. So it took her a total of 4 minutes on the subway. Okay, so we're going to spend lots of time with functions, lots of time looking at some of these graphs and reading them, tables, graphing functions. They're pretty cool. So we're going to spend a fair amount of time with them in this unit, and then we're going to explore some other functions later on in the year. All right, nice job, guys.